Welcome to Test-Driven Development with Twisted, presented by a company I have with Jean-Paul, who's sitting in the back. We do Twisted consulting and training and support. Some contact info. If you would like to follow along the slides, there's a link here, which you can load the slides into your computer. At some point, I'm going to take this down, but it may be a while. We'll probably be up for a while. So the way this class is going to work, there's about 45 minutes or so of lecture, followed by a hands-on exercise. Or, depending on what you're doing, possibly 2 hands-on exercises. So, to begin with, how many people, can you raise your hand if you've actually written code with Twisted? Okay, so about half audience. So this is supposed to be a, due to lack of time, we can't do both an introduction and a class on test-driven development with Twisted. And so this is supposed to be more of a class which is teaching, assume some knowledge of Twisted. Perhaps if you read the documentation, that will suffice. But there is some assumption that either you know Twisted or you can learn it on your own. So that's the bad news if you don't quite know Twisted. The good news is that I've tried, at least some of the taught material, I've tried to make it more general. And the labs themselves are exercises where I've written the tests for you. And what you're going to be doing is following the tests and making them pass one by one as you do the exercises. And for those of you who have less experience with Twisted, there's going to be 2 labs. If you already know Twisted pretty well, you might want to just skip straight to the second one. For those of you who know Twisted less well, there's a simpler exercise to begin with. There will be unit tests to guide you what to do next. And sitting in the back, there's Tom, Ashwini, Jean-Paul, and Mashek. Did I pronounce that correctly? Yes. And along with me, we'll be walking around and helping people. And so you should have a lot of hands-on help. So depending on what level of experience you have, I believe you should be able to get something out of this class one way or another. If you don't know Twisted and I'm talking about some specific Twisted API and how to test it, don't worry about it too much. You'll be working your way up to the more. Welcome to Test-Driven Development with Twisted, presented by a company I have with Jean-Paul, who's sitting in the back. We do Twisted consulting and training and support. Some contact info. If you would like to follow along the slides, there's a link here, which you can load the slides into your computer. At some point, I'm going to take this down, but it may be a while. We'll probably be up for a while. So the way this class is going to work, there's about 45 minutes or so of lecture, followed by a hands-on exercise. Or, depending on what you're doing, possibly 2 hands-on exercises. So, to begin with, how many people, can you raise your hand if you've actually written code with Twisted? Okay, so about half audience. So this is supposed to be a, due to lack of time, we can't do both an introduction and a class on test-driven development with Twisted. And so this is supposed to be more of a class which is teaching, assume some knowledge of Twisted. Perhaps if you read the documentation, that will suffice. But there is some assumption that either you know Twisted or you can learn it on your own. So that's the bad news if you don't quite know Twisted. The good news is that I've tried, at least some of the taught material, I've tried to make it more general. And the labs themselves are exercises where I've written the tests for you. And what you're going to be doing is following the tests and making them pass one by one as you do the exercises. And for those of you who have less experience with Twisted, there's going to be 2 labs. If you already know Twisted pretty well, you might want to just skip straight to the second one. For those of you who know Twisted less well, there's a simpler exercise to begin with. There will be unit tests to guide you what to do next. And sitting in the back, there's Tom, Ashwini, Jean-Paul, and Mashek. Did I pronounce that correctly? Yes. And along with me, we'll be walking around and helping people. And so you should have a lot of hands-on help. So depending on what level of experience you have, I believe you should be able to get something out of this class one way or another. If you don't know Twisted and I'm talking about some specific Twisted API and how to test it, don't worry about it too much. You'll be working your way up to the more test-driven development. And why should we care? So we can begin with why do we want to test our software? So we want to test our software because things are going to change. The requirements are going to change. We're going to find some bugs in our code. The libraries we depend on are going to change. Someone's going to release a new version of the programming language, which is slightly different in lots of minor ways, and so we're going to have to upgrade to using it. And moreover, people aren't perfect. Even if you understand your code right now completely and utterly, and personally I usually don't once it gets complex enough, you may not remember in 6 months from now what exactly you were thinking when you wrote that code. You may be working with colleagues who you're collaborating with. You don't know quite what's in their head. They don't know quite what's in your head. And realistically, if you're working on a large project, someday you're going to be asked to fix a bug in a piece of code you've never seen that was written by someone 2 years ago, and they've left the company, and they're living in a small island of the Pacific, so they can't be reached for questions. So you have to deal with the fact that your knowledge of the software and how it works and what its requirements are is not perfect. But we need working code. We need our software to keep working in the face of change. We need to be able to change our software and have it not break and still meet whatever the requirements are. So a test is, in some sense, a specification. It is an automated way of saying, my code should do this in this situation. It should do that in that situation. And when you run this automated set of tests, this specification encapsulated in code, sometimes the tests fail, and that failure tells you where something is happening that shouldn't be happening, where there's a bug, you're not supporting some feature you need to, something is wrong. And so that is how tests function once you've already written the code. But what if we haven't written the code yet? What if we're developing the software? If we can consider tests as a form of specification, then if we wrote the tests before we wrote the code, if first we wrote the tests, and then we wrote some code, and now the tests pass, that means we know when our code is ready. We know, oh, we now meet the specification because all our tests pass. So the way you do test-driven development is in some sense very mechanical. First, you define a small unit of work, and you write a test for it. You make an assertion. You say, when I do this, something exciting should happen, but not too exciting, something very specifically exciting. And then you run the test. Since you haven't written the code yet, your test is going to fail. If you wrote the test and you ran the test and it passed, then something is wrong because this feature is not supposed to have been implemented yet. You haven't fixed the bug yet. So either you misunderstood the code or your test has a problem. So we want our test to fail. Then we implement the unit of work. We add the feature, we write the function, we fix the bug, and then we run the test again. And when the test passes, we know we're done with this unit of work, and we move on to the next one. And so it's a repetitive, somewhat mechanical process. At the same time, test-driven development can be seen as a much more expansive and useful way of doing things. You end up with better code and better tested code. Okay, just want to make sure it's not a slide I'm missing. In particular, you end up with better tested code because since you start out with writing the test, you don't have to go back and say, oh, I have this pile of code. How do I write tests for it? How do I make sure it works correctly? From the very beginning, the first thing you're doing is thinking about how to write tests to prove your code works. And so, and in addition, you cannot implement a feature. You can't fix a bug. You can't write a function without first writing a test for it. So inherently, you end up with code that's much better tested. Moreover, if you're writing tests after the code, you have to be sure that the test is testing what you think it's testing. And so if you write some code and then write a test and then the test passes, you can't quite always be certain that you've proven that the code is correct. So what you have to do is you go back and you break your code slightly. And then you run the test, and then the test fails. And you fix your test, and your test succeeds. And thus proving that the test is actually doing what you think it does. And so if you write the test first, and you always go from failing to success, you don't have to do that trying to break your code step. And in addition, and this is a less explicit benefit, and harder to prove, but I do think it's the case, test-driven code leads to better design because it forces you to think more about what your API boundaries are, what the abstraction levels are, how am I going to separate things into self-contained components so I can test them in isolation. And so I believe that that tests also lead to better API design and better structured code. So some principles, either for doing test-driven development or for software development in general that merge in with test-driven development. You should write libraries, not applications. Even if what you think of is writing is what you think of as an application, if you're not going to be using any shared code, separating out in your code the parts that are reusable functionality, that are generic, that are general, that aren't specific to the way you write files to the file system, and then from the other part of the code, which is how do I tie everything together, is a very useful thing, both in terms of design and making reusable code, but also in terms of testing. For example, if you have a configuration file that your code loads, if you hard code the path in your middle of your library code and then always load it, it's harder to test because it's going to want a test file to be in that particular path. And it'll be harder to repurpose that code for some other environment or for some other use. Whereas if you pass the configuration in and then your application code knows about loading the configuration file from the specific location, it's much easier to write tests. You have more reusable code. Your tests should be self-contained as much as possible. Every time you depend on an external resource, on a database, on a network server, on anything but the inner state of your program, you're making your tests more fragile, you're making them less predictable, and you want your tests to be as predictable as possible because when you're debugging, you don't want each test run to be different. You want each test run to be identical. And so your tests should, insofar as it's possible, be as self-contained and restricted and in memory as possible. You also need to write a different set of tests, of course, which do interface with external resources, like talk to a database or do an end-to-end test with all your different servers in a realistic network. That's really a different type of test. And today we'll mostly be focusing on unit tests and not about functional or end-to-end tests. And the worst kind of external dependency is an external dependency that is on the internet, like sending a request to yahoo.com. Because if it's a database, at least you can set it up in your local machine. If it's like google.com that you're sending a request to, if you don't have an internet connection, you can't run your tests. So if you do feel the need to use external resources, at least try to make it resources that you can set up on each developer's machine. Not always possible, but these are best, what we aim for at least. Each test should test one unit of work, which is a bit hard to define, but At the extreme, you might say you should only have one assertion in each test. So you should test successes separately from failures. Try to keep your tests as small and self-contained and specific as possible. So that's some theory about test-driven development. And let's look at a worked out, very trivial example, but a bit more concrete than what I've been saying so far. So we have a class record, which has some information in it, not a lot of information, and we want to store these records in a database of some sort, and then at some point later retrieve them from the database. This is going to be a relational database. We'll write a little bit of SQL. So the first thing we do, and this is a simple case, so we can just do it in our head. In a more complicated case, we might write a little sketch using code, and then we'll throw out the code or comment it out, because again, we're writing for the real code, we're going to write the tests before the code. So we do a sketch, not real implementation. And here I just did it in prose in my head, basically. And so we want to do really two operations here. We want to take a record object and insert it to the database using a SQL insert command. And then the other thing we want to do is be able to retrieve records from the database by running a SQL select command. That's how you retrieve records. And then you get a bunch of rows. We're probably going to use the Python database API. So each row is a list of items that came out of the select query. And we're going to parse those lists into record objects. And so if you'll notice, the second thing we want to do, the retrieval function, has two parts to it. First, we run a select statement, and then we parse the results. So there's two actions here. There's two verbs, two parts. And so we're probably going to want two tests to test the two separate parts of this operation. Whereas in the first operation, inserting, there's only one action. And so probably we'll have maybe one test. If we start thinking about failure cases, then there's more. But just thinking about the successful, we're inserting a record. Okay. So the next step is we take that sort of high-level sketch of how things are going to work, and then we write down the tests that we wish to write. So I'm not worrying about failure cases here. So we want to write one test, which is that the record storage.insert method takes a record and then runs an insert statement based on it. There is a parse rows method on record storage, which takes a sequence of lists with two items in them and converts it into a list of records. So that's the parsing functionality we'll be testing. And then there's a third test that we have a retrieve function that runs a select statement and then calls the parse function with the resulting rows and returns the result of whatever that parse function did. And then parenthetically, because it's a bit out of scope for unit tests, we're probably going to want some end-to-end tests with a real database where we insert a record and then retrieve it and make sure the inserted record is the same as the one we retrieved. But we're not, that's assumes we have a database, and so it's sort of a different category of test. By the way, if anyone wants to ask a question or interrupt me, just do so at any time. So,
how can you be sure that the tests you write reflect the reality of a database API?
That's why we have the functional end-to-end test as well. So we have the series of tests where we are going to emulate a database. And then there's a final test where we say, we're just emulating a database, we might be doing it wrong. And so we'll do something that actually runs it in a realistic environment in the real database. And that will catch any problems where we made a mistake or we thought we were testing the right thing and we aren't. Because tests are code written by imperfect people. The tests are not perfect.
How do you know that your test does not contain bugs?
You don't? You might notice your test has a bug because you ran it the first time and it passed. You might realize your test has a bug because you wrote some code you know absolutely is correct. And then you ran the test and the test failed, and so you'll stare at them and you'll say, oh, the test is wrong. At some point, or you may find your test is buggy because a month later something goes terribly wrong and you realize you didn't think you were testing what you thought you were testing. Beyond a certain level, if you could, the only way you could prove your tests were absolutely correct was by writing tests for your tests, but then you had more tests, and so.
So are you actually saying that 1, 2, and 3 aren't really operating on a database?
That is correct, and that's what we'll see in the next example, and when we actually start writing the tests.
Yeah, I got a question about the second test.
Yeah?
So you're testing your private implementation.
Yes.
Why would you do that?
You would do that because if you don't know how your private implementation is part of your code, and if you don't test it, you won't know that it's correct.
But isn't it being tested indirectly through your public?
It's being tested indirectly, but ideally your public interface is as small as possible. And so there may be far more private code than public code, and so it seems better to have just as much tests for it. But also, when things go wrong, it's very helpful to be able to pinpoint exactly where the problem is. If you only have high-level tests, and the high-level tests go through 500 lines of private functionality that doesn't have isolated tests, it's harder to pinpoint where exactly the problem is. And so by testing very small units of work, it makes it easier to find problems. And finally, we want to have as quick a cycle of validation of the correctness of code as possible. If you only test public APIs, you may have to write a lot of code before you can write the tests.
Your tests are now linked to your implementation, which seems like you're writing brittle tests.
To some extent, well, you can. To some extent, your tests are more brittle, but you can separate them out into these are the tests that test the public API, and perhaps in a more generic way, because you might have multiple implementations of the public API. And this is the test class that tests private implementation details. And so when you change the private implementation details, you can only worry about those tests. And the immediate feedback for is my code working or not is very helpful. In the example I'm going to work out, the test I wrote found 3 typos in my code. If you have to write like 5 functions before you can run a test, it takes longer for you to find the bugs, and so by the time you're debugging them, there's a lot of code to figure out what's going on. And the most public interface are probably the things you're testing with the end-to-end test or the functional test, and those functions are often for applications at least, those are the ones you really care about, less so than library code. John Paul, would you have any other points to make? Okay.
Make smaller assertions if you're testing less amount of code. And
Yeah.
so having testing private implementation details, you know exactly how that's going to work. Yes, you'll need to change it, but it allows you to make more precise tests.
Yeah. So the brittleness is a fair point, and it's probably I should probably like in the examples the labs you'll be doing, there's a little bit of that where I partly as a form of guidance, I'm testing in detail a lot of things, and there's no real separation between the private and public API tests, and so that does restrict how you can implement things a little bit. And so I will certainly keep that in mind for future code I write to maybe separate the public API tests and the private tests more explicitly. Any more questions? Okay, so we had step 1, sketch implementation, very high level. Step 2, write a list of tests. And notice the list of tests is closer to the way the code's going to work. So we're going from a sort of high-level description of the operations to things that are closer to actual code. And so next, we're actually going to start implementing these tests one by one. So let's implement a test. And we're going to use Python's unit test library, which lets you write test cases and make assertions. We import our record class, we import our storage class, and then we implement a fake cursor, which emulates the API that a Python DB API database cursor would implement, or implements just enough of it that you can pretend that you're running a SQL statement against a real database. So we have a fake cursor, and when you execute a statement, it's going to store that statement for later. It doesn't do anything else. And so here's our first test. It has a docstring. Your test should always have docstrings with some prose explaining what it is you're trying to test, separate from the actual code, so that if you later come back and you figure out, you read the code of a test and you say, this test makes no sense, you'll have that description in prose rather than code saying this is what the test is supposed to be testing. And so you can write a sentence, understand what's going on, or realize that the code is wrong. And you'll notice that that docstring on that test function is exactly the same as the text in our list of tests from the previous slide. So our list of tests become more or less the docstrings for the tests we're going to implement. And so we have a test method. We create a fake cursor. We create an instance of our storage class. We insert a record by calling the insert method with a record. And then we assert that the cursor had executed on it the SQL statement insert into records idrow values, and then to values, and then with the appropriate values, the ID and value of the record object we passed in. So that's our test. Next, we run our test. We're going to use Python's built-in test runner because we don't need anything fancier. We run the test. It fails. There's no code there to do anything. So as expected, we get an error. So next, we're going to implement our code. So the record class was already there. Now we're going to implement the code, some code in the record storage class. So our init method takes a cursor and stores it. And then write an insert method that executes on the cursor a SQL statement inserting the record. And now when we run the test passes. More accurately, when I wrote this, I ran the test and it failed because I had 3 different typos in my initial implementation. I was sleep deprived. Probably you're not introducing 3 typos into every 5 lines of code you write. But in more complex code, realistically, you will often, at this point, write code you thought was perfect, and your test will have found a bug or something wrong. So you go over your code, or occasionally you'll find that your test is buggy at this point. But hopefully your test was right. If not, you'll fix the test. If the code is buggy, you'll fix the code, and now you get to the point where you have a running test. And what you do now is you move on to the next test on your list. Implement the test, run it, it fails, implement the code. Eventually the test will pass, and repeat. So the exercises you'll be doing today are test-driven in that the tests have actually been written for you. And so you won't have to rewrite the tests, but you should be paying attention to how the tests work, the order the tests were written in, and so on. When you're doing the labs, you should, of course, be editing the code, not the tests. People have done these labs before, so they've pointed out bugs in the tests, and then I fixed them and I upload a new version so other people can use it. But if you think you found a bug in the tests, let me know and I can take a look. Excuse me. Always read when you're implementing the labs, always read the doc string for the test, because that will explain in prose what it is you're supposed to be testing. You need to be careful not to write your code to the test. The purpose of your code is not, while it is to make the test pass, it should make the test pass in a sensible way. You can often make the test pass in a non-sensible way by matching exactly what the test is doing rather than the intention of the test. And so you should read the test doctrine to see what it intends. Read the test implementation details rather than just looking at the exceptions that come out. There's initially going to be maybe between 5 and 20 tests failing. So you might want to run the tests one by one so you don't have to scroll through vast amounts of tracebacks. And throughout the code, there's also comments with hints about what APIs you should be using and so on. So that was the section on test-driven development generically. Does anyone have questions about that? Yes.
Do you have any pointers? A lot of times when I'm trying to make fake stuff, like you had the pretty simple example of the fake person. A lot of times my test code ends up being much more complicated than the code I'm testing.
So for the labs I wrote, and I wrote them using test-driven development. So I wrote a test, implemented the code, repeated. I believe the unit tests are about twice as long as the actual code they're testing. And I did not actually implement any fakes, or not much.
So
It's not uncommon for you to have a lot more test code than you have actual code, because you have to test all the different cases. So you have to test the success, failure, and the success case and the failure case. And you might have to test for bad input, and so on. And so there's a lot of different situations you have to test. And you might build up some scaffolding so you don't have to be as repetitive. The tests I wrote don't have as much scaffolding, in parts just for readability, so you can read each test on its own. So scaffolding, or having a single, a verified fake, a fake who you've written some tests for on its own because you're using it so much to make sure it's the same as a real thing. And we'll be presenting a couple of those in the next section. Or standard pre-written fakes that you can reuse in library code. But it is often the case that test code is much longer than the actual code. So next we'll talk about testing in the context of Twisted, using trial, which is a package providing testing utilities for Twisted, and also a command line test runner, similar to the Python test runner or Nose or other test runners you may have seen, although as far as I know, it predates all of them. So you'll recall that I suggested that unit tests should, as much as possible, not depend on external resources. And one of the resources we don't want to, for writing network code, writing a TCP server, writing a UDP client, what have you, it would be ideal if our network code, the code we're writing to deal with the network, didn't actually rely on a real network in order for us to be able to test it. That means we have less sources of failure, even if we're running over loopback. Even if we're connecting back to the same process using TCP, you still have to worry about firewalls. We've seen occasional bugs where like FreeBSD jails break multicast. Windows pops up a firewall warning when you run your test, that sort of thing. So ideally, and again, simply by asking the operating system to deliver bytes for you, the operating system may deliver the bytes in a different order than you expected, which makes testing certain edge cases harder. In TCP, there's no guarantee that the writes will match the data. The order will be the same, but the bytes that the receiver receives are not necessarily the same match up with the writes that the writer wrote. So if you do 2 writes, they might be delivered as a single read on the other side. So you want completely deterministic tests. And so Twisted provides a number of utility classes to help out with testing your network code without actually having to talk to the network. So here's an example network protocol. You might use it with a TCP connection. So we initialize it, and it has a buffer, which is a string, and a list of lines. And every time this protocol receives some data from its transport, from the way it communicates with the world, data received will be called without those bytes. And so if you've seen socket programming before, you will do like socket receive to read the bytes. But that requires you to have a socket object in your hand. Whereas this protocol doesn't know where its data is coming from. It just has a data received method. So it's easier to use it with other sources of data than just sockets. You could use it with a serial port, or with standard in, standard out, or, as we'll see in a moment, with a transport that's simply in memory and is basically just storing bytes in memory. So every time you receive some bytes, we add them to the buffer, and we try splitting that buffer into lines by splitting on carriage return line feed. Any bytes that we have at the end of that resulting list of lines are bytes that belong in the next line, so we keep them for later. And then for each line we've received, we recall line received. The reason we need to buffer data, again, is the bytes that you'll be receiving in this protocol don't necessarily match up with the bytes that were sent from the other side in terms of their boundaries. So even if the writer has just sent you a single line in a single write, you may receive only half of that line in each data received call. So you have to accumulate data in your buffer until you've gotten all the data you expect. So for each line we call line received. We store each line received in a list, and then we write back to the transport. To the other side of the connection, we write the number of lines we received so far. So the first line we receive, we write out 1. The next line we receive, we write out 2, then we write out 3, then we write out 4, and so on. So does this code make sense to everyone? Excuse me, I have a cold. So let's imagine you received ABC/R/N and then X. So X belongs to the next line. So if you split on /R/N, you'll get a list with 2 items in it. ABC is the first item, as X is a second item. So the last item in the list is always the bytes that are at the beginning of the next line. If you have a full line in your string, then it'll be the empty string. So if you have ABC/R/N and you split on /R/N, you'll have ABC empty string. And then your buffer is just the empty string. So the bytes, the last bytes when you split are always the bytes that are part of the beginning of the next line that you have not received fully yet.
What prevents you from losing that X then?
You do self.buffer equals lines. You'll see that self.buffer equals lines that pop -1. So we keep it on self.buffer, and then the next time we get data, self.buffer will have those bytes.
So even though you reset the buffer variable to lines without the last one, it magically remembers it? I'm missing something there.
You're removing the last item from the list of lines.
And it doesn't come back in ever. That X was already transmitted.
Yes, and then you store it in self.buffer.
Popping off the last one.
Yes, you pop off the last item and you store it in self.buffer as the beginning of the next line.
Yes.
So this, in practice, you don't have to do this because Twisted has a class that does this for you, and you'll be using it in the second lab. But I did this just for educational purposes.
Is there a specific reason you didn't use split lines?
Because split lines uses the operating system line endings, and network protocols have very specific definitions of what a line ending is, which is often /R/N. And for a network protocol, you have to match the network protocol, not what your operating system or Python happens to think a line is. So let's write some tests. So the first test, there should be a docstring here, but lack of docstring makes the test fit better on the slide. Less code to read. So we create an instance of our protocol, and we create an object called a string transport. In a real application, our protocol would be hooked up to a TCP server, a TCP client, a serial port, something. For our test, we don't want any of those. We want string transport because that gives us a transport that keeps everything in memory, which means it's completely deterministic. We can write unit tests using it. And then we call make connection on our protocol, and that's how you connect a transport to a protocol. Typically, the twisted framework will do this for you, but since we're writing a unit test, we have to do it manually. And now we call data received as some bytes. And so if we want to test what happens when you receive some data, you just call a function. You don't need to fake a socket object and worry about dealing with edge case socket errors that only happen on Windows. Just call data received. Some bytes are delivered to your protocol. And then we assert that if you deliver 2 lines to the protocol, it will have split those 2 lines and stored them on its lines attribute. So that's the first test. The second test we write actually uses the string transport class. So we create an instance of our protocol. We hook it up to a fake transport. And then we deliver some bytes to that protocol instance. And then we assert that the value of the transport is 1/r/n. So the value function of strings transport returns the bytes that have been written to that transport. And so we're asserting that the bytes 1/r/n have been written to the transport, which is what we expect because we're writing out as each line is received, we write the count of how many lines we've received so far. And then when we deliver another line, we see that 2/r/n was appended to the transport. And so we've made an assertion about what bytes our protocol writes out. So we can test the behavior when you pass bytes in, and you can make assertions about the bytes that the protocol writes out. And again, we're not using sockets, we're not using TCP. It's all completely deterministic. There's no event loop. Twisted is a networking event loop, so it's driving things for you. This is not an event loop code. There's no reactor object. It's completely linear. Just call this function, assert this thing happens. Call that function, assert this thing happens. Completely deterministic. So is this making sense so far? Okay. So next, we'll talk about deferreds. For those of you who haven't seen them, deferreds are a way to wrap a callback. It's a way of saying, I have a result. I am going to do a task on your behalf. You requested me to do something, and there's your response, but I don't have the actual result yet. So I'm going to give you this placeholder called a deferred, and sooner or later, that placeholder is going to have a result. And then if I ask someone to do something on my behalf and they give me back a deferred, the way I use it is I say, when you have a result, call this function with it for me. The actual I taught a 2-day class on Twisted, and the actual introduction to deferreds is a lot longer than this. So if this isn't quite making sense to you, that's fine. There'll be a lot to do. Doesn't involve deferreds. But we have a protocol. It accepts the deferred as an argument. And then every time it receives data, it accumulates those bytes. And eventually, when it gets 10 or more bytes, it says, OK, I've got the first 10 bytes. I'm going to take those 10 bytes, and I'm going to push them into the deferred, thus indicating to anyone who's waiting on it that we have finally gotten the result that they were waiting for. So we want 2 different tests here. One test is, if we have received less than 10 bytes, the deferred should not have anything in it. If we haven't finished the request, we haven't gotten 10 bytes, the deferred should not have anything in it. Once we've gotten 10 bytes, the deferred should have those first 10 bytes in it. So we write 2 tests. These 2 tests only work in Twisted 12.3 or later, which the majority of you will not have on your, if you're relying, for example, on the Mac OS X Twisted, it's very unlikely that you have 12.3. So the next slide, we'll see the other way of doing this. So you'll notice we're inheriting from a different test case class. We're inheriting from twisted trial unit test synchronous test case, which is a subclass of the Python test case that adds some extra utility functions that are twisted specific. So for the first test, we create a deferred, and when we instantiate our protocol with that deferred, and we deliver 5 bytes to the protocol. Since 5 bytes is less than 10 bytes, you then assert that the deferred doesn't have any result in it. Our protocol is only supposed to give us a result if we've done 10 bytes or more, only 5 bytes, we assert there's no result. In our second test, we again create a deferred, create a protocol that has a reference to it, and then we receive first 5 bytes, and then another 7 bytes, and now we've received 12 bytes. And so we call a function called success result of a deferred, and it extracts whatever the deferred has as its result. It's called success result of because deferreds, like the Python stack, can return things both as success results and as errors, much like throwing an exception. So we want the success result, and we assert that that is equal to the first 10 bytes that the protocol received. So we can make assertions about the current state of a deferred and get back an immediate result and make assertions about it. Any questions about this?
Why is it called synchronous test case?
There's a base class of a class that inherits from synchronous test case called test case, which is twisted trial unit test case, which we'll see in a couple slides, which actually uses the event loop, and which lets you do asynchronous operations that don't just involve running one function, and when the function is done, the test is done. And so that's an asynchronous, although for shorthand, it's just test case. When we were starting the port to Python 3, we split that functionality into 2. And so if you inherit from synchronous test case, it doesn't know anything about the reactor, is the main difference from the regular twisted test case. So you can just inherit from the twisted.trial.unittest test case, that test case, and just ignore synchronous test case. But if you do know the twisted APIs, it emphasizes this class does not involve the reactor anyway.
So it's just like regular unit test.
With some extra functions. You'll see that there's extra functionality involving running tests, which is not in the next class, which is not present here.
Yeah, I was just curious, if you're using synchronous test case, can you just run it with Python built-in?
You can actually run any of the Twisted's tests with a Python built-in runner.
Oh, really?
Yes, or with nose or whatever. Because they all inherit from Python's test case class, so it's all the standard API for tests.
They're not going to know anything about the reactor unless you use that.
Well, they do. But Twisted's test runner has other functionality, which I'll mention in a bit, that is related, that you probably, for Twisted test, you often want to use Twisted's test runner because it has some extra functionality that is tied into Twisted. If you have a older version of Twisted, and you're going to see things like this in the labs you write, there is no assert, no result, or success result of. So you basically, what you do is you make a list, and you say, when this deferred has a result, call list.append with that result. So we do deferred.add callback, result.append. And then we make assertions about the contents of that list. So we say is, for example, in the second test, we create a deferred, an empty list, and we create a protocol that wraps the deferred, and we say, add callback result.append, i.e., when this deferred has a result, call this function with that result. And then after we've delivered 12 bytes, the deferred will have a result. It'll call result.append, and now result will have the first 10 bytes as it's the first item in the list. So this is sort of a verbose way of doing what the previous slide does, which makes a lot more sense in terms of readability and semantic meaning. But older versions of Twisted don't support it, so the labs you'll be seeing do it the second way. Another thing we might want to test is the passage of time. In this example protocol, we are saying after we store it with a reference to the reactor, the core event loop object named twisted, which has methods like connect TCP, listen TCP, and also call later. So we say, we have a protocol, and after the connection is made, we're going to schedule an event to happen in 3,600 seconds in an hour, which is close the connection. Transport.lose connection means close the connection. So what we're saying is after an hour, that whatever you have a TCP connection to this protocol, after an hour it's going to close it. You usually want to do this for timeouts. You send a request to the server. If you don't get a response back in 30 seconds, you assume the server is not there and you close the connection. So we want to test that this function schedules something to run in an hour. But we don't want our test to sit there for an hour. We could do this by just waiting. We run this code, and then we run the event loop, and an hour later the connection will be closed. That's tedious. And so we want to simulate the passage of time. And again, Twisted provides a utility class that does this. And the utility class is called clock, twisted.internet.task.clock. So we create a thing we call a reactor, which is the clock instance. Just so we know that we're pretending it's a reactor. We create a protocol which has a reference to our fake reactor. Create a fake transport. And then we hook up the protocol to the transport. And initially we say the transport is not disconnecting. The transport's connected. The disconnecting flag is a attribute of the string transport, fake transport. It's there for testing purposes. I'm not sure that a real twisted transport actually has it. It might, but we're using it in here for testing purposes. Then we advance time 3,599 seconds, and we're still not disconnected. Now we advance time 1 second, we hit an hour, and now we assert that the transport has in fact disconnected by doing assert true. And since we're only using a fake implementation of time, this does not take an hour, it takes however many microseconds, I guess, it takes to run this code. A blink of an eye, certainly. So any questions about this? Okay. So the twisted trial unit test case class, which you'll be seeing in the sample test we've written, has a bunch of additional functionality for testing twisted classes, twisted code. If you log an error using Twisted's logging system in the middle of your test, that will make the test fail. If you're logging some unexpected value error or attribute error or what have you in the middle of your test, the code that the test is running, that probably indicates a bug in your code. So unexpected exceptions being logged makes your test fail. If you're using the event loop, if you want to use the twisted event loop, and we'll see an example in a bit, you can return a deferred from a test or from setup or tear down, and Twisted will run the event loop until that deferred has a result in it. And so you can actually run the twisted event loop as part of your test. And there's a bunch of extra utility methods that assert failure, at least, we will cover. Others you can see by looking at the API documentation. So this example is less of a unit test and more of a functional test.
So in the first test case that you had where you were using a deferred, is it because you're using because normally that would, with the add callback, it would be run asynchronously. Is that because
Nope.
you're not using the event?
Deferreds have nothing at all to do with the event loop.
Okay, so
Deferreds are completely deterministic in what they do. There's nothing, if you read the implementation of deferreds, I believe, I'm not sure if it even imports the Reactor module. Deferreds are just a way to turn a callback inside out to say the order in which I run a function with the result and when I have the result can be in either order. And so when you say add callback, all you're saying is if you have a result already, call this function immediately. If you don't have a result, when you do add the result, it'll call you. But that doesn't require an event loop. It just requires a little bit of state on the deferred. And so those tests deliberately do not use the event loop because you don't need an event loop to test deferreds. In like 2 slides from now, you'll see an example of using deferreds. It does require the event loop because we're waiting for a result. Mostly deferreds involve the event loop because the thing that's going to put a result into the deferred requires the event loop. So if the deferred you have is the result of downloading a web page, you'll never have a result until that downloading the web page finishes, which requires the event loop. But if you're manually pushing it in, you don't need an event loop for that. So this is an end-to-end test. We're going to start up a real web server and a real TCP, a real web client, and have them talk to each other over TCP. So we have a resource object, which is just how you publish pages on Twisted's web server, and it's just always going to return hello. It's just a very trivial web server. And so we start a web server on port 0 by doing reactor.listen TCP. Port 0 means allocate a random port. If we hard-coded port 8000, then we couldn't run 2 tests at the same time because they'd both be trying to run on the same port. And so we asked the operating system to allocate a random free port for us. And we add a cleanup. We say, use the Python test case add cleanup to schedule a function to be run after the test, which stops listening on this port, so we don't have any state left behind. We extract the real port number. We're listening at a random port, and so we need to figure out what it is. And we use that port to construct the URL of this web server we just started. So we have a function that starts a web server that will publish the string hello. So every time if you point a browser at it, you'll see hello. And returns the URL in which that web server can be reached. And then in our test, we start the web server. We call twisted.web.client.getPage with that URL. We use Twisted's HTTP client to retrieve the URL. We say, when you have a result, call this function called getResult. And then getResult asserts that the result is equal to hello, exclamation mark. So we assert that our HTTP client downloaded from the HTTP server the string hello, exclamation mark, which is what we expected to get. And the important thing to notice here is we're returning the deferred that we created. By returning a deferred, we are indicating to Twisted that this test requires the event loop. And so rather than just, usually when you return from your test function, the test is over. Because we inherited from the right class, from Twisted trial.unittest test case, and returned a deferred, Twisted does not consider the test to be finished when it returns, if it returns a deferred. Instead, it considers the test to have finished when that deferred has a result. So when the deferred has a result, which is, it'll call a getResult, and then when getResult is done, control will pass on to the test framework, and the test framework will say, oh, this deferred finally has a result in it, this test is done. And so you'll see a couple of examples of this in the labs you'll be doing where I actually start up a real HTTP server and point a real HTTP client at it. But it's only in those those are just sanity check end-to-end tests. Every other test you will see in the tests you'll be working with today do not involve the event loop at all. Any questions about this?
What happens if the result never comes?
It'll time out after a couple minutes, or a timeout of your choice. And this is, again, another reason why this sort of test is not as good as one might hope, because it can take an arbitrary, when things go wrong, and you might notice this when you're debugging your code, you will occasionally just have the end-to-end test just hang, and it's much harder to debug than the other tests because it's not clear what went wrong.
So this is not a good test, right?
It's a necessary test. You might want to have a different set of tests running in a different way for the end-to-end tests. And also Twisted has tests that use a reactor internally for historical reasons because we haven't. But sometimes once you've, beyond a certain point, you need to be testing things more realistically because you haven't thought of everything. So testing with a real HTTP client might find bugs in your HTTP server or assumptions you made that you wouldn't have thought of otherwise. And if it's from, or your code is talking to a relational database, and at some point you have to talk to a real database. You can't. There's only so far you can fake it. So for your end-to-end tests, they will be more fragile. They will break more often. And so maybe you want to run them separately or have a server whose job it is to run them for you rather than have developers do it. But you do have to have them as well because there's only so far you can go. And eventually you have to talk to the real systems and make sure your assumptions are correct. So we're tracking a bit slow, but it's okay. You can also assert, beforehand we asserted that deferred has a failure, had failed right now, or we could assert that deferred has a success right now. Assert failure lets you say, I assert that this deferred will eventually have a result, which is this error. So we expect a HTTP error. I'm going to skim this because if you know Twisted, you can figure it out. I don't think it shows up in the labs, and I would like people to start coding. But yeah, so if you log errors in your test, they will make your tests fail unless it's, but sometimes you deliberately log the exception. For example, if you're testing what happens when you get bad data. And so you want to say, when I get bad data, I return this result and I log this exception. So there's a utility method on the test case that's called flush logged errors that says, I expected you to have logged this exception. And it returns a list of the exceptions that it logged. And so you can indicate that in this particular case, if you got a bad data error that was intentional, don't consider that a test failure. And I mentioned the second item as well. Trial also provides a command line.
So it just checks that at the end of the test case method?
You typically do this at the end of your test, yeah. And there'll be an example in one of the tests you're using. Twisted has a test runner called trial. You can give it the name of a package or a module, or you can do a full path to my package.mymodule, .myclass.mymethod, and we'll do that specific test. I recommend doing that when you're doing the actual lab. But you can say, run all the tests in my package. It'll find them and run them for you. It has, it writes out the twisted log to a file. There's a command line that lets you choose the reactor. Not really relevant to you. There's a -b command line, which you might find useful today, which jumps into a debugger every time an error is logged. I don't mention here, but there's a -e, or real-time errors flag, that prints out, rather than waiting until the end of the test run to print out all the errors, prints out the errors as they occur. And again, that might prove useful to you today. I think it's -e. If you run the trial -minor help, you'll see a bunch of useful help explaining all the different command line arguments. And there's a how-to with documentation covering much of what I've said here, if you want to refer to it later or at home. Very long prose description and working out of various test-driven development with Twisted. So I recommend reading that. It's part of the core Twisted documentation. And you can read the API documentation for Twisted, which also provides some information. So we have 2 labs today. Both of them involve writing HTTP servers. The first lab involves writing the world's most minimal HTTP server. It just absolutely the minimum it needs to figure out how to respond to a HTTP request. The second lab is a much more extensive. You're building up a real HTTP server with a pluggable backend that supports both synchronous and asynchronous operations with error handling and so on. If you haven't used Twisted before, I would recommend starting with the first lab. You can also, but it's up to you. So just this is a very, very quick review of the HTTP protocol so that you get a sense of what it is you're working on. So HTTP is how your browser talks to your web server, and it's a request-response protocol. Your HTTP client or browser sends a request to the server, gets back a response. So requests are of the form verb, typically get, but you're submitting a form, it might be a post or it might be a put. So you have a verb and then you have a path. So if you're going to www.example.com/index.html, you'll have a /index.html as a second argument in your first line. There's the version of HTTP you're talking, and then there's line ending, carriage return line feed. And then there's a bunch of headers, which are key, colon, value. There might be spaces in the value, there might be colons in the value. It's the first colon that tells you where to split. And then there is an empty line indicating that the request is over. Assuming there's no request body, which is you may only deal with it at the end of the lab. So the way you can know, unless there's some extra header in there indicating that there's a request body, you know that their HTTP request is over when you get that empty line with no header in front of it. And so the first lab you're going to write is going to recognize HTTP requests ending solely by the fact that they're going to find an empty line at the end of your data. It's not going to do any more parsing. And the second lab, you're actually going to parse HTTP requests the way a real HTTP server would. And in response to this request, the server sends back to the client a response, which is of the form version of HTTP, a response code. 200 means OK, 404 means not found, 500 means internal server error, and so on. The third thing you see on the first line of the response is a string. For example, this is a good response that says OK. The string does not have any semantic meaning at all. It's just some text. And so in the web server you're going to write, you're just going to hard code that string because it really means nothing. Then we return some headers, and these headers actually have some meaning. So we say, this is going to have a content type of plain text, and it has a length of 5 bytes. And then again, we have a new line, empty line, indicating the end of the response headers. And then we have the body of the response. And since we said it's 5 bytes, we have exactly 5 bytes of content after the response. And that's an HTTP response. Any questions about that? OK. So the first lab can be found here. There are some instructions there's a URL where to download it. Some instructions on how to run trial on Windows. Some useful information. Does anyone not have those slides in their computer? So if you replace, I'm going to go forward and backwards, so you might want to have it in your computer as well. So if you replace the URL you see there, and then you replace that part with tdd.html. So www.futurefoundries.com/pycon13/tdd.html. That will get you to the slides. But we can come over and help you with that in a minute. So this is the first exercise, what you might want to start with. The second exercise is more advanced and uses more twisted. Again, you implement an HTTP server, making tests pass one by one. You should try to have one test passing before you move on to the next one, so that you're not just trying to do 3 things at once. So you're sure that you've gotten previous parts of the code working before you move on. So once you're going through the second lab, but maybe in the first one as well, you should maybe pay attention. This is not the main goal, but depending how new the actual APIs are, you may be able to do this. Notice how the tests are trying to test one thing at a time. The tests match the order, more or less, in which I implemented them. So I start from simple functionality. You can actually, after doing only a third of the tests in the second lab, you can actually point a browser at your server, and then another third through you get more functionality. So It builds up over time. There's some end-to-end testing in there. There's separation of library code and application code. The logic for parsing bytes, for parsing the HTTP protocol, for generating the HTTP protocol is separate from the business logic of what do I do once I've gotten the request. And this is always a good principle. You should separate out different concerns. Parsing bytes and deciding what to do with them should be separate. You need to if you're writing network applications, you have to handle errors. You'll see tests in there for various error cases. The web server has timeouts in it in case the client it's talking to is malfunctioning. Some of the ways, the patterns of using deferreds in the server, if you get that far, is a pretty common pattern. And again, there's a final slide here with download information of this second lab and how to run the tests and so on. So I will leave the slide up with the first lab, but if you have the slides on your computer, you can just go forward and download the second lab once you're done with the first one. So again, there'll be a bunch of us walking around helping people out. If you are stuck on something, so we've got about, well, how long do we have? I'm not sure how long we have. As far as, like, we definitely have until they kick us out of this room. But I think 2 hours might be approximately what we have. There's supposed to be a break in the middle. Since everyone's going to be, from this point on, just working, feel free to go out any time. And when you're done, there is a tutorial at the end that PyCon would like you to fill out about this tutorial. Please do it at the end. And I will remind people to do so when we're done. Okay, so any questions before we move on to the actual hands-on exercises? Yes?
So, question about trial. Is it just test run online?
Yes, it runs the tests for you.
That's all it does?
Yes, it is only there to run tests for you. It has a bunch of functionality to make running tests. Like it does different output, and it has debugging functions running. You can jump into debugger on test failures and so on. So it's a lot of functionality for running tests, but it's just there to run tests, and that's all. I'll walk over in a minute. Okay, so yeah, if you get stuck on anything, raise your hand. One of us will come by. Don't try. You should try to figure it out on your own. But if something just completely doesn't make any sense to you, that's what we're here for. And the more you ask, the more you learn, the more you'll be able to make progress and continue in the exercises and learn both about twisted and testing. Okay.